Hello there, I'm Morgan. I'm in the Spintronics and Photonics group at the University of Glasgow, and my supervisor, Hayim Macedo. I'm going to talk to you a little bit today about spin dynamics and magnon-photon coupling. I'm also a member of the Centre for Doctoral Training in Photonic Integration and Advanced Data Storage. The CDT is spearheaded by Queen's University Belfast, the University of Glasgow, and the Irish Photonic Integration Centre, and is a vibrant research community that strives to foster collaboration between researchers dedicated to understanding and developing technology that is critical to modern society. So onto the spin dynamics. We can learn a lot about spin dynamics and spin resonances just by analyzing the semi-classical torque equation. So we'll forget all about quantum mechanical spin for the moment and just consider this as a bar magnet with angular momentum. So when we apply a static magnetic field in the vicinity of this spin, it will experience a torque. So in the first instance, we can think of this infinitesimally. The spin feels a torque which rotates the tip of its vector in an infinitesimal arc, and at each infinitesimal point further in the arc, it feels this torque again, which is what gives rise to this precessional motion. This response has an intrinsic frequency quantified by the gyromagnetic ratio gamma, which is very much dependent on material properties. If we have a one-dimensional chain of spins, we have to consider the exchange interaction, which for a ferromagnetic material will tend to align the spins in the same direction. This exchange interaction is much stronger than any other interaction between the spins, dipolar interactions for example, and below the Curie temperature essentially means these spins constitute an effective medium that can support spin waves. Also, in many magnetic materials, spins are considered good approximation as localized to the atomic lattice sites. So you have a spin lattice where all these spins are connected by the exchange interaction, which leads to an effective spin medium through which all kinds of these precessional waves can propagate. So we see here in the example, for any spin, the spins either side of it will act to tilt that spin in their direction. Thus we have a difference in where these vectors are pointing at each position along the chain. And so we have a difference in the phase of the precessional motion for each of the spins, represented as a dispersion along the chain. And so there will be particular frequencies that these spin waves can be excited at. It's important to mention here in the first instance that precession is a response to this static applied field, but in reality we have damping which will make this precessional motion relax into the equilibrium position in a spiraling trajectory, where our equilibrium position is modified by anisotropy and subject to small fluctuations due to thermal effects. This relaxation typically occurs on nanosecond timescales. So if we're looking at any longer time scale, all this static field does in a way is supplies the energy or availability for these modes to exist, and then you have to actually apply a driving field which can couple to the transverse directions of this motion to actually excite the specific modes. So we have a spin medium which is activated by an applied static field, and then you can drive many different modes of these spin waves with an appropriate oscillating field. So the various effects and interactions between the spin waves and the static field and driving fields can all be included in equations of this form. And we gave an example for a single spin here, but you can very easily define your magnetization as the sum over the spins divided by the volume, which gives you an identical equation for the magnetization vector. So going on, how do we supply these driving fields which are resonant with these spin wave modes? In the cavity magnonics community, there are a few currently favored ways of doing this. At the top here, we have some 3D cavity resonators, within which we have an example of YIG spheres. YIG is one of the most favored materials at the moment because it's very low damping, which gives the magnons a longer lifetime. Anti-ferromagnetic materials such as hematite are also being studied, and I've been looking at permalloy in these setups. So on the left, going down anti-clockwise, we have an example of 2D resonators, such as split ring resonators, transmission lines, coplanar wave resonators, and so on. The essential idea is that you have a shorted waveguide that can support standing transverse electromagnetic modes. And so we'll have a particular field profile, and so we know how the fields are going to be acting on our magnetic sample at specific positions in the cavity. These systems are usually analyzed using VNA FMR, and reflection or transmission measurements can be performed. We can draw an analogy between the cavity resonators for the photons and the magnetic materials for the magnons as both supporting intrinsic modes and both being able to excite these modes in one another through Faraday and Ampere's law. So we see here an example of a cross-section of a T21 mode in one of these 3D cavity resonators. In the middle here we have a one-dimensional field, which can be very useful if you want to analyze things in terms of a dynamic susceptibility, because then we only have to consider one component of that susceptibility tensor. In certain scenarios we might want to consider more complex fields acting on our sample, but it's useful that we can do things one-dimensionally as a first case. And here on the right we have an example of a coplanar resonator, and again we have this one-dimensional field in the middle, and both of these can be modeled quite readily in COMSOL. So going back to the magnons, as I mentioned, we can consider the magnetic material as a spin medium capable of supporting various modes. The fundamental mode in this instance is called the Cattell mode after Charles Cattell. The response of spins to a driving field at the fundamental frequency is for all the spins to precess in phase. So relating back to the dispersion across the chain earlier, in this instance the wave number is 0. If we take the example of a Higgs sphere, we can consider this as a macro spin moment with a precession frequency given by this simple form of the Cattell equation here. So along with the AC fields of our microwave resonators, we essentially now have under consideration two coupled oscillators. We can gain some insight into how these oscillators behave when they're interacting by going back and looking at classical harmonic oscillators. So if this is our cavity photon system on the left, we can think of this stiffness constant as being related to the damping of the photons in the cavity, and so describable by its Q factor. And likewise on the right, if this is our magnal system, then the stiffness is just the Gilbert damping. And then if there's some coupling kappa between them, for example, if we have our Higgs sphere inside the cavity at the correct frequency, the graph on the left here shows what we would see for no coupling between the two systems. We can imagine this being the case if our cavity frequency is far from the precession frequency, whereas on the right we see what happens when we have some coupling. We get this level repulsion, which is typical of coherently coupled oscillator systems. Going back to the magnons and photons, you can see here on the left an example of a cavity resonance. So it's just the absorption spectra of an unperturbed cavity, which is obviously not dependent on an externally applied field and just resonating in one of its modes. Then on the right of that, we have an FMR spectrum, which just follows the linear increase that we see with the Cattell equation. So if we put this now inside the cavity, then we see this level repulsion typical of these coupled oscillators. And we have a splitting of the absorption and a continual exchange of energy between these two systems. So what we have is this hybrid FMR cavity mode, which is normally dubbed as the cavity magnon polariton, and the coupling between the two is very tunable in general. So here we can see an example just by changing the position of a Higgs sphere inside a 3D cavity, we can increase or decrease this coupling. I just wanted to draw attention to two areas of application which might be linked to great effect in the future. So in 2015, Nakamura's group achieved indirect coupling between a superconducting qubit and ferromagnetic magnons through the cavity photons. What they had is a 3D resonator within which you have a similar field profile to what was shown earlier, but in addition to the magnetic fields, you also of course have an electric field, and you have regions within the cavity where you have a higher magnetic field and no electric field, to very good approximation, and vice versa. So you can position your sphere at a point inside the cavity where it will couple to this magnetic field, and you can position your qubit at a position where there's no magnetic field. Then the electric field will drive the Rabi oscillations of this qubit, and so the photons in the cavity are driving oscillations in both the ferromagnet and the qubit simultaneously. This is perhaps the first step towards engineering an entanglement between magnons and superconducting qubits. Also, Nakamura's group in 2016 showed that by taking advantage of the Faraday effect, microwave to optical conversion could be achieved. And this has been demonstrated again in 2020 by Kim's group, where they did this not just for the Cattell mode, but also for the higher order spin wave modes. So we can imagine here the foundations of potentially being able to couple superconducting qubits to optical light. And if that could be achieved, then the foundations of a quantum internet are in place. So that's a very exciting area of ongoing research, combining these two seminal works, both very much focused around the cavity magnon polariton. There are many other potential applications of these cavity magnon polaritons, but I just wanted to draw attention to one of the most exciting areas. Thank you very much for listening.